ones that we've done, but I want to point out what I think would be the best strategy. I want to point a couple other things out as well. What is the operation between the 2 and the parentheses right there? Is it addition, subtraction, multiplication, or division? It's multiplication. What is the operation between the parentheses and the 3 right there? Isn't it also multiplication? So to me, this is where we could use the properties that we've discussed to make this a little bit easier for you. Do you remember with multiplication, it's commutative? That means you can like mix the order all around and that's okay?
Yeah.
What I think I would do, what I'd elect to do here, is I'd multiply the 2 times the 3 first. Because I can. The order does not matter with multiplication. So I'd multiply the 2 times the 3, and that for my first step would give me, of course, 6, parentheses 4a plus b minus 9. There we go. And now, doesn't this look a little bit more like a typical distributive property? Like it doesn't have 2 numbers being multiplied, and it just has the 1 number. So now at this point, I think I would choose to distribute the 6 in there. When I multiply 6 times 4a, what does that end up being?
24a.
That's right. And then I multiply the 6 times the b. Of course, that's 6b. And are you guys good? 6 times negative 9?
Negative 54.
Negative 54, yep. So we get that distribution property settled there. We should be in good shape. You don't have to do the 2 times 3 first. You could distribute a 2 and then distribute a 3. But I'd rather just do it in one shot. Okay, any questions? Okay, the last one up there is a little bit weird. Do you think number 14 really is a distributive property? Or have I kind of thrown a little bit of a curveball at you? What do you think, Victoria?
It's a distributive property because there's a 1 in front of the parentheses.
That's a good point. So what she's saying, I think, is that there's technically a 1 right there. And so Victoria is right. Technically, what's being distributed is a negative 1 times everything in the parentheses, and so that's what we'll do. What's negative 1 times 4a? Jake? It's negative. Because it's a negative times a positive, it's negative 4a. Avery, how about the other distributive part there? Negative 1 times negative 5. So plus 5. Most everybody handles this part okay. Some people forget that the minus sign gets distributed over there to the second term as well. So be careful with that. You should be in good shape. All right. So our final topic of this chapter, and then we'll be out of kind of the review part of this this year, is like terms. And so I want to discuss this with you, and then we'll be at the board, I think, for pretty much the whole rest of our time. Sweet. It should be fun. All right, so here we go. Here we go. Okay, so we'll do a little bit of talking, a little bit of work, we'll be at the board. Here we go. So we're going to talk about like terms and what you can do with them. And I've got this little chart here that helps us kind of identify like terms. And so what makes 2 terms like terms are they have to have the exact same variable, and then they have to have the exact same exponent on that variable. So for example, just a contrast here, 4x and 7x are like terms because they both have an x, and more specifically, it's x to the first, right? The exponent is the same on both. You look over here, these are unlike terms. They both have just one variable, but one of the variables is an x, the other one is a y, so they are unlike terms. What you can do with like terms is you can combine them by addition. You cannot do that with unlike terms. That's why this is important. Take a look over here. A little more complicated looking. Negative 10p squared and 25p squared. Those are like terms because they both have the exact same variable and they have the exact same exponent on that variable. This one's a little trickier on the right. They both have the same variable, the letter p, but one of them is p to the first, the other one is p squared, making them not like terms because although they do have the same variable, they have different exponents. On the left, even more complicated, 1/3 c cubed d and c cubed d. Well, the 1/3 is a little bit weird, right? They've got the fraction in there, but that doesn't really matter. The only thing that matters as far as whether they are like terms or not is do they have the same variables and do they have the exact same exponents on those variables? And the answer is yes. Over here, you see that the answer to that question is no. On the left, you've got a c cubed and a d. and on the right you have only a c cubed. You're missing the d, making them unlike terms. Maybe you've seen that before. If you have, that's great. If not, this is what unlike or like terms mean. So let's take a look at numbers 15 and 16. If you guys could take a minute and work on your paper there with your table, with a partner, and make sure that you guys agree on numbers 15 and 16. I simply want you to circle the like terms. That's it, using what we just talked about. All right, Joel, would you decide? Hey guys, we're going to get started here. Joel, what'd you decide on number 15? Did you circle any terms?
Oh, yeah, negative 8b and 4b.
So guys, you want to pay attention to this. Joel decided to circle negative 8b and positive 4b. Why did you circle those as being like terms?
They're the same variable and, yeah.
And? Yeah? Anything else to put on the end? Same
they're-
variable,
They don't have any extra variables,
right?
and it's to the same power,
Yeah, and what is that power here?
0.
That's actually 1. B to the first. But Joel, I do have something I want to mention though. Did you guys see that the first term is negative and the second term is positive? Doesn't that make them unlike terms? Are you sure? They're still like terms. The positivity or negativity of the coefficient makes no difference whatsoever. It simply has to do with the variables, right? So they have the same variable and the same exponent of the variable. Joel has done a good job. Any questions? Okay, Paige, what do you think about 16? What did you circle on 16?
I didn't circle anything. I didn't think there was any like terms.
Oh, okay. Why not? See a bunch of X's, right?
Yeah, but some of them are to like have different exponents, and
Okay.
then the last one, like XD.
So it's got the extra variable. So Paige is definitely correct. She's done a great job, and you did a really good job explaining why you picked that answer too. It's well done. So there are none for number 16. There are no like terms there for all the reasons she said. Do you have any questions about that? I'm happy you seem like you're confident. Okay. So now we are going to do something with this like term stuff. Whoa. Don't you love the irony of injuring yourself on crutches? All right, so here we go. We'll do a couple of these here. Get these down in your notes. Really think about these. We'll do these at the board here in a little bit. Please ask questions if you have them. So combining like terms. So if you have like terms, you can combine them by adding them up. And here's what you do. It's got it right up here. When combining like terms, the variable remains the same. So if it was an x, it stays an x. It doesn't become like x squared or something like that. If it was a z, it stays a z. It doesn't become like a z squared or z cubed. So the variable remains the same, and the coefficients are added. So here's what we would do with a problem like number 17. First of all, did you notice that all those terms are actually like terms? They all have b to the first for their variable. So what I'm going to do is I'm simply going to add up the coefficients, which are negative 20, negative 9, and 12. So let's see if we can do this together. What is negative 20 plus negative 9? Negative 29 plus 12. Negative 17. So when I add these up, I could write this out as negative 29b plus 12b. And then I add those up and I get negative 17b. So notice it didn't become like b squared or b cubed or something like that. The variables stay exactly the same, but it's the coefficients that you're adding up. This is when you are adding like terms. If we were going to be trying to multiply these together, things would be different. If I was going to be dividing these, things would be different. But I'm adding them, adding these like terms, and so this is how we do that. We good? Why don't you guys try number 18 all by yourselves, or work with a partner. Number 18.
I'll be the school.
At number 18. Of course, 18, what's the big scary thing about 18? Fractions. Kind of scary, but if you look at it, they are like terms, right? So all you really need to do is add the coefficients, and I was nice enough to make the coefficients already have a common denominator. Ashlyn, what'd you get for number 18?
I got 7G.
18.
Oh,
I think you combined that with number 19.
sorry. I got 7/15.
7/15. C, 7/15 C, definitely correct. She added the coefficients correctly, and you left the variable the same. It's unfortunately it's really common. People will sometimes say C plus C is like C squared, right? And so we want to be really careful with that. You did a good job. Cole, how about number 19? 13G minus G.
12G.
Nice job. Okay, so that is correct. Can you see why someone would do this? You watching? In fact, at some point you might have been guilty of this in the past. 13G minus G, 13. Do you see why somebody might think that? 13G, take away the G? It's not what it means, right? That's not what the math means, but you want to watch out for something like that. And Cole, can I come back to you? Where did the 12 come from, really? I see a 13 and some G's.
You have 13. If you were to have like 13 G's,
Yep.
and if you get rid of one of the G's,
How many do you have left? You have 12 of them. How do you know there was one G that you took away? Because I don't see a 1 in there anywhere.
It doesn't say 2 G's. It just says G.
So if there's no coefficient given, we understand
It's an invisible one.
it's an invisible 1, right? And that's where you got that 1. So it really is 13G minus 1G, technically is what it was. All right. You all seem comfortable and confident? So the last one obviously looks more complicated, so we're going to do this one together. You'll get a chance to practice ones like that at the board. So here we go, number 20. There we go. All right, so Kendall, can we save the grooming for later? I appreciate that. So there's a lot going on in here. What jumps out to you as something that we could start to break this down and simplify it a little bit? What if something kind of jumps out at you like, oh, I can do that? What do you see, Grace?
The 11a squared minus negative 7a squared.
I agree, and I think if I were doing this one, I might do that first as well, but can we do that last? That's actually a really good idea, but I want to illustrate something. But you've identified some like terms. I completely agree with you. I really do. But let's save that for later. Is that okay?
Yeah.
Okay.
You can distribute the 5 into the 2a.
Yeah.
7.
I think that's where I'd go first here, at least for today. So we distribute the 5. Grace, keep going. When you do distribute the 5, what do you get?
10a minus 35.
10a minus 35. We have plus 11a squared. Let's keep going with this. Hosanna, what do you see on that next set of parentheses? What could we do to kind of simplify that? Say again?
Negative, positive.
Okay, so tell me exactly what I should write.
Negative 4a, or no, positive 4a, minus 9 minus 70 squared.
What did you use to come up with that? Yes, that's exactly right. You distributed, right? Distributed that minus 1 across the parentheses. That's perfect. So here's what I wanted to illustrate for you guys. When you end up with a longer string of terms, sometimes using color coding or shapes, you've probably seen the shapes thing, to help you identify your like terms is a good way to go. So here's what I'm going to do. I am going to start by circling. So I see 10a. We kind of did this earlier. What I'm going to do is I'm going to look through the rest of my expression here and ask myself, are there any terms that are like 10a? Do you see anything that's like 10a? Ashlyn? 4a is like it. I agree. Anything else? Are those the only two like terms as far as a goes? That's it, right? Okay, so 10a plus 4a is? 14a, yeah. So we'll go ahead and add those up. Once we have done that, I'm going to look through the rest. There's obviously a bunch of other terms left over. So I'm going to put a box around negative 35. Is there anything that is like? Yeah, negative 9, right? We keep the sign with it. Mm-hmm. So negative 9 is like negative 35. When I add those up, what do I get?
49. 45.
44, negative 44.
That's what I said.
4 does kind of look like a 9. Okay, so that just leaves our last two. And so maybe we use, I don't know, like a triangle or something for these. So it's going to be positive 11a squared. Is negative 7a squared like 11a squared?
Yeah.
It is. So we could put a triangle around those. And so the idea would be to match the shapes together, just kind of a visual to help you associate the correct like terms together. Okay, so then what is 11a squared plus negative 7a squared? Positive, yeah. So it'd be positive 4a squared. Okay, so that would be it. The only other thing I would add to this, are you guys used to writing answers like this in descending degree or descending exponents? So some folks are comfortable doing this. They'd write 4a squared plus 14a minus 44. You guys see how the exponents on the variables decrease? 2, 1, and then no variable. So you don't have to do that. It would be good practice later on. It'll be pretty handy for you to do it that way. At this point, I don't really care. Just know that later on it might be helpful to have that habit in place. You're done with one chapter. Isn't that cool? Yay! So let's practice. Well, this has been all review, right? So it's time to start making it make a little more sense for algebra.